So now we are going to describe the ballot-based leader election algorithm. So what are the desirable properties? We will allow a process P to inaccurately leave a correct process as long as the new leader has a higher ballot number. The most important thing is that we get an agreement on leaders with higher ballot numbers. Lower ballot numbers we can ignore. We will also require that a process is elected as a leader only if a majority of processes are correct and alive, and that is actually fits sequence Paxos, because sequence Paxos does not make progress anyway before we have a majority that are correct. These are the two important properties that we want to make sure that we always satisfy. Eventually, every correct process trusts some correct process if a majority are correct. This is the new condition we have. This is what we call completeness. The other property is that no two correct processes trust different correct processes. Eventually, of course, because of our partially synchronous system. So eventually we are going to have an agreement. So what is our assumption? We assume a fail noisy model. So processes may fail by crashing and initial arbitrary network delays, but eventually the network stabilizes and we get a partially synchronous system. We also assume perfect links. However, this is only initially assumed. In fact, the algorithm works for a weaker model where network may drop messages and processes may crash and recover. We are not going to prove the algorithm for this weaker network condition, but you can look for yourself and see that this is true. So what is the basic idea? Ballots are unique. That's a very important thing. So every process P has its own ballot, and the ballot is a number and a PID of that process identifier. This pair is always unique since the PID is unique and it comes from a totally ordered set. Second, the ballot will constitute the rank of a process. And the idea of this algorithm, which is a rank-based algorithm, that processes will compete and the one with the highest rank will win. Max ballots are available at each correct process. So each correct process periodically gossips its ballot to all processes. So as long as the process is correct and the network is fine, each process will have information about the max ballot. And as I said, processes are ranked, so eventually every correct process will elect a process with the highest rank, and that is the max ballot, given good network conditions, and that is eventual agreement. We are going to require a majority are correct to be able to elect a leader. So each correct process will trust a leader only if the leader's max ballot is among the collected ballots from a majority of processes. Second, we have a monotonically increasing ballots. So every correct process that do not receive the leader's ballot among collected ballots, consider the leader has crashed, and it will start a new election process where P increases its ballots to a number higher than the current ballot of the considered crashed leader. We are going to satisfy unique ballots that are monotonically increasing, and also completeness assuming eventual synchrony. So each process, as we said, is ranked by N and PID, and N is an increasing epoch number, and PID is a process identifier. At any epoch N under stable network condition, the correct process with the highest PID is the leader and remains the leader if supported by a majority. And periodically, say with a delay delta, each process collects the ballots of correct processes and disseminate the known max ballot max. The algorithm works as follows. So each process will be either in 3 states: a follower, a candidate to become a leader, and is a leader. So each process starts as a follower, which is this state. Periodically, each process collects ballots from a majority to check the leader. And as long as the leader is alive, the process stays as a follower. So here is a case where the leader is detected. If the leader's ballot is absent after collecting ballots from a majority, we came to this situation, then we're really starting now a new election. The process PI moves to become a candidate. It increases its own ballot number to have a value higher than the max ballot. And this will be done by each process. And the one with the highest rank wins and is elected. So this is the max ballot wins. And one becomes a leader. All the others go back to become a follower. And also, if a message from a suspected process is received, the delay is adjusted, normally by increasing the delay to a certain bound. This is a basic algorithm. So here is the algorithm now, and you're going to get the code of this algorithm, the pseudocode. So we have a ballot leader election. We use a perfect point-to-point link, and everybody starts at round 0. Empty ballots, your own. You start with your ballot is your own identifier and 0, of course. You don't know the leader, and the max ballot is your own ballot. And the delay is delta, and you start a timeout. We are going now to check this in a nice way. We are going now to see what happens when timeout occurs. The first thing is this statement here. Forget it for a while now. Let's look to the rest, and we will come back to it. So you reset the collected ballot to 0, and you increase the round number, and you start a request response pattern here. So for all processes except yourself, you send a heartbeat to the process. This is your current round to identify the request reply pattern, and you disseminate what you know is the max ballot, and you start a delay. If somebody got the heartbeat request in round R with the max ballot, so it will update its max ballot here. This is updating the max ballot to the one that is highest, and then it will send a heartbeat reply with its own ballot. And when the requester receives a heartbeat reply, and if it is for this round, you add the ballot to the collected ballots. Now we are here collecting ballots. But if R is not equal to the current round, then it means we are getting an old message. To this guy, we did not really define our period correctly. So we adjust the delay. Now let us go back to this part here. And this says if we collected now a ballot from a majority, so it means the ballot I collected plus my ballot is greater than a majority, then we go and do check leader. Check leader will do two things. It will first see if the leader is among the ballots that we have here, so everything is fine. But if the leader is not among the ballots that we collected, then things are wrong. He might have been dead. And in this case, we try to bump up, increase up our ballot number. Now let us look to procedure check leader. So we have collected ballots now. So we pick up the max ballot among these collected ballots. When you do that, we get a top ballot and a top process. This is, we call it top. If the top ballot is not the max ballot, we know that the max ballot is the ballot of the leader, then we suspect the leader. And what we do, we increase our ballot number by increasing the epoch to a ballot that is higher than the ballot max. And we set the leader to unknown, which would mean we are really starting a new election process. If, on the other hand, the max ballot is equal or higher than the top ballot, then we execute this code. We check if the top is our leader, then we do nothing. But if the top is not our leader, so we update our ballot max. We say that the leader now is a top, and we trigger the leader to the higher process, which basically is saying now we have a new election. This is the top process, and this is the top ballot. You can see here each process gets an automatically increasing ballot number with new leaders, so that is fine. And also you see is that when we did not detect the ballot of the leader here and we increase our ballot, in the next round we will get a new top. That's guaranteed. And so a leader election will actually then take 2 rounds. One when you pump up the ballots, and the next one when everybody detects that and elects the new leader. So now we have an algorithm that satisfies eventual agreement, since the period will increase so that heartbeats are delivered to each correct process by each correct process. The second is once a leader crashes or gets disconnected from a majority, this majority will increase its ballot to get a higher number and that of the leader. And in the next round, one of the processes in that majority will be elected based on the highest rank. And that will satisfy then eventual completeness, because eventual completeness says eventually every process trusts a leader. And of course, this ballot will be higher, so we have this monotonic ballot property. And if you think about it, the algorithm works even if messages are lost or processes crashes and recovers. And this is because we periodically do the gossip of the max ballot and our ballot numbers. So if a process is disconnected for a while or the message has been dropped, then he will catch up later. And that concludes the algorithm.